Problem relaxation is what decides how to create heuristics. A standard approach of creating heuristics is to relax a problem by adding some new actions. By relaxation, we mean having actions possible in the problem space which is not there in the original problem, but then the idea of adding these actions is such that to get to a solution, you do not need search anymore. The solution cost that I get can be directly computed without a search, and that solution cost in the relaxed problem gives me the heuristic function. Heuristic created as relaxed problems are usually something called admissible. We will look at little while later what we mean by admissibility of a heuristics. But first let's look at what we mean by problem relaxation. Let us assume that we have the 8 puzzle game. The 8 puzzle game, in terms of its original actions, has only 4 operators which are just going right, left, up or down. When I was counting the displaced tiles, I was not looking at these 4 operations, but I was looking at a relaxed problem of the whole idea. The idea being that I assumed that I could take each tile and put it in its original position. In such a way, getting to the goal from the start was not about searching for in a graph, but trying to understand how many times I have to pick up things which are not in place and put them there. But before that, we want to understand what we mean by admissible heuristics. So a heuristics is admissible if it never overestimates the cost of reaching a goal from any node. So in that case, the null heuristic, which returns 0 for any node, is also admissible heuristic. The only thing required for a heuristic to be admissible is that it never returns a value greater than the actual cost and to the nearest goal from any node. Let's say Hn is an admissible heuristic. Hn is admissible if and only if Hn is less than equal to H star n, where H star is the true cost to reach the goal from the current n. An admissible heuristic never overestimates the cost to reach the goal. That is, it is optimistic. So let us look at problem relaxation and try to understand how heuristics are created. Again, falling back onto the 8 puzzle game, here we have the start state given to you on your left, and on the right is the goal that I want to arrive at. Now one needs to understand that in an 8 puzzle game, all we can do is move tiles from one place to another, or if and only if there is a blank. So the only possibility in this game right now is to move 5 this side, move 6 here, move 2 down there, or move 3 up. Those are the only possibilities. But in a relaxed game, I would be able to do more than that. So we can transform it into any state on the right. The only action is about not sliding them like this, left or right into the empty spaces. So in a relaxed problem definition, what we would be more interesting to do is to find out how many tiles do I need to pick up basically to give it to this side. So in this problem, in a relaxed state, if I could be able to pick them up, so I would love to have 7 picked up and put here. That's one operation. I would love to pick up 2 and put there. So that would be another operation, 1 plus 1, 2 operations. I would love to pick up 4, put it here. That would be 3 operations. I would love to pick up 5, put it there, 4 operations. Pick up 6, put it in its place, 5 operations. pick up 8, put it in its place, pick up 3, put it in its place, and pick up 1 and put it in its place. So I would have 8 operations required to move from this to this in a relaxed problem, where the relaxation is about picking them up. So basically I was counting how many tiles were misplaced so that I could pick them up and place it back. I could look at the same thing in a slightly different way. I could assume that these tiles that I have are actually in different 2D planes. In that case, I should be able to individually move them in x and y directions. So, like, let me give you what I mean. Like, if I want to bring 7, which is here, to here, so I would be able to take 7 from here to here in number of 1 and 2 step, and take 7 from here to here in number of 1 step. So I would be taking 3 steps and bringing 7 to its position. I would be able to take 2 here and bring it here in 1 step. So this is another form of heuristics that we will look at, where instead of counting the misplaced tiles, I am trying to count the distance that is there in terms of moving it along the x and y axes. So this is how we will look at a relaxed problem. A relaxed problem with fewer restrictions on the action and is possible. So cost of an action solution to a relaxed problem is admissible heuristics for the original problem. This is what makes a problem relaxation important. If the rules of the 8 puzzle game, as I was trying to explain, are relaxed, that a tile can move anywhere, then I give the shortest solution because I pick up every tile and put it in its original position. If the rules of the game are relaxed, that a tile can move to an adjacent square, then that gives me again another shortest solution and to give me 2 heuristics. So let us look at the first heuristic called the number of misplaced tiles. Suppose we take out a tile and place it in its correct position, as I was trying to explain you in the previous slide. Given any state, question is how many moves I would require to come to this state. It is precisely the number of misplaced tiles. This is also called the Hamming distance. In this relaxed version of 8 puzzle, we do not need to search to find out a solution. We can calculate it directly, so it can be used as a heuristic. This heuristic is called the heuristic of number of misplaced tiles. Let us call it as H sub 1. The other heuristic that we were talking of is the heuristic where I assume in a relaxed state that each tile can move in its 2D plane, and these 2D planes are stacked one above another to make the whole problem. So 7 can move from its current position and up there, come down to this level and then move here onto this level. For that matter, 3 can go from here via this to this. So suppose we can slide a tile into any block as opposed to only the empty block, and given any state, question is how many moves would I need to come to the goal state. Now if you look at it very closely, you could realize that it would be the total of how many steps each of the block requires to be moved. So like 7 here requires 1, 2 and 3 moves, 3 requires 1 and 2 move to it reaching its position, so on and so forth. We could calculate the total of these distance. This distance would then give me the total cost required to move from this given start to this given goal state. This distance that I have calculated, the sum of the vertical and horizontal distance of each tile from its desired position is also called the Manhattan distance. So the second heuristic that we have now named is the total of the Manhattan distances for each of the tiles. Let us try to understand it for the 8 puzzle problem more better. So we have now two heuristics. One, the number of misplaced tiles, and number 2, the total Manhattan distance. Let us try to calculate each of them. Calculating each of them has been explained previously, but let us try to get that clear here. So for the first heuristic, I count how many tiles are misplaced. So if you see, 7 is not in its place, 2 is not in its place, 4 is not in its place, 6, 1, 3, 8, 5. None of them are in its place. So the total number of misplaced tiles here are 1, 2, 3, 4, 5, 6, 7, 8. So the number of misplaced tiles is 8. So the heuristic value is 8. Expectation is that, now remember what an heuristic value is. It is an estimate from the current state to the goal state. So expectation is that by taking some 8 moves, I would be able to go from here to here. Let us look at the second heuristic, the total Manhattan distance heuristic here. So let us look at each of them one by one. Let's take number 1. Number 1 in the current state, if it has to reach number 1 in the goal state, we'll have to make a move of 1 step, 2 step, and the 3rd step. If I take that route, or for that matter, 1 step, 2 step, 3 step, if I take that route. So basically number 1 would need 3 steps to move to its goal position. Number 2 in the current state would only need 1 move to reach to the goal position. So here it is, so only 1 move to reach to the goal position. Number 3 is here, and in the goal it is on the left middle. So I should be able to move 3 here and go 1 step this side. So I have 1, 2 steps for 3. For 4, I have, let me clear this so that you can see it more clearly what is happening for 4. So for 4, or here is the goal position and here I am in the initial state. So in order to move to the goal position, I would need 1 step coming down and 1 step going left. So I would need 2 steps. Or if I take the other route, I would be like 1 step going left and 1 step coming down. So 2 is the number for number 4. Number 5 similarly would be 1 step and 2 steps. Number 6 would be 1 step, 2 step, and a 3. So 3 steps. Number 7, let's count number 7 here, 1 step, 2 step, and 1 step more, so 3 steps. And number 8 is, if you see, has to be pushed to the extreme right, so 1 step, 2 steps, so 2. So the total number of moves that is required for the Manhattan distance heuristic is 18. So the estimate that Manhattan does is that 18 steps possibly would be required if I have to move from the given start to go to the given goal. In fact, later on we will see that neither the misplaced tiles nor the Manhattan distance has given us the accurate measure. If you want to play this game, you later realize that this is more than what has been estimated by the misplaced tiles as well as the total Manhattan distance. So now let us look at what we mean by admissible and what we mean by inadmissible heuristics. Inadmissible heuristics are pessimistic heuristics. They overestimate the cost. And on the other hand, admissible, as I have been defining, are optimistic heuristics because they underestimate the cost. Later we will see that admissible heuristics can only slow down search by assigning a lower cost to a bad plan, but not very dangerous. Whereas inadmissible heuristics break optimality by trapping good plans. Now let us recall from our previous lecture what we mean by an optimal solution. An optimal solution is, for the given solutions that I have, if I can get the minimum cost solution, that's an optimal solution. So let us look now more closely on how inadmissible heuristics breaks optimality. Suppose node A has been expanded and I get two nodes B and C on the fringe. Now if you look at the cost of the nodes C and B and try to understand which node to expand, you will see that this cost is made up of two different costs. One, which is the exact cost of the current node that I arrive at from the start node, and the other is an estimate of how much I need to spend to go to the goal. At A, because it is the start node, the actual cost of coming to this node is 0, whereas the heuristic estimate is given as 5. The branch that's coming to C, the cost is 1, whereas the branch that goes to B also has a cost 1. So if I compute the total cost at C, it will be like the cost of coming to C, which is 1, and the heuristic estimate of going from C to the goal, which is 2, 1 plus 2, that's 3. And if I look at B, the cost is of course 1, but the heuristic estimate that I make of going to the goal is 4, making the total cost of node B as 5. So in this current scenario, node C will be expanded next. So we expand node C. That is what will happen. So when node C is expanded next, what will happen is that I will arrive at goal G, and now this goal will be taken off the fringe because now I will see that I have arrived at the goal. The total cost of the goal that I will get in this case is the total cost of coming by this path, which is 3 plus 1, 4. If you now look at this problem very closely, you see that because I have used an heuristic which give 4 here and 2 here, I got a path which the total cost was 4. Whereas on the other side, I did have a path where the total cost was less than 4, which is 3. Question is, why did not I get this path and got this path? This is precisely because of the following reason. We have estimated here that the cost to the goal would be 4, whereas the actual cost was only 2. We made an overestimate. Making an overestimate spoiled this path for us, and therefore we were not able to get the optimal solution. A more expensive path, which is of cost 4, was given to us instead of the cheaper path, which is A, B goal, which is at the total cost of 1 plus 2, which is 3. This happened only because our heuristic function that we have used overestimated the cost of the path B to goal. Any heuristic function that overestimates is a pessimistic heuristic function, and we call it an inadmissible heuristic. An inadmissible heuristic therefore breaks optimality, does not lead to a path which is the minimum.